In this video, we'll be discussing an application of exponential equations, exponential growth and decay. The mathematical model for exponential growth or decay is given by a equals a sub 0 times e to the kt power, where a sub 0 is the original amount or size at time t equals 0, a is the amount at time t, and k is a constant representing the growth or decay rate. If k is a positive number, the function models the amount or size of a growing entity. But if k is a negative number, the function models the amount or size of a decaying entity. You'll definitely need to know this formula. In 1990, the population of Africa was 643 million, and by 2000 it had grown to 813 million. Find the exponential growth function that models the data in which t is the number of years after 1990. We'll round our k value to 5 decimal places. Then we'll use that equation to determine by which year Africa's population will reach 200 million or 2 billion. That's 2,000 million or 2 billion. So let's start by finding the growth model. We're going to be using the equation a equals a sub 0 times e to the kt power. This is very similar to solving variation problems, where you start by writing your equation, which we have right here. Then you use the given information to find your k value and rewrite the function including that k value, then using that function to answer a question. Very similar process to that. So let's see what information we were given. In 1990, the population of Africa was 643 million. So that's our initial amount, our a sub 0. By the year 2000, it had grown to 813 million. Well, this is our a, our amount at time t. Well, what's time t? We went from 1990 to the year 2000, so these two numbers together tell us that t is equal to 10. I have every variable except k, so we're going to plug these three numbers into our equation and solve for k. 813 equals 643 times e to the k times 10 power. I'm just going to rewrite that exponent. 813 equals 643 times e to the 10k. We have an exponential equation to solve here. We start by isolating the exponential. 643. We'll divide each side by. Uh, 813 divided by 643 does not go in nice. We get a decimal, but we don't want to round on the first move of solving our equation, so we're going to leave the fraction. We're not going to be able to rewrite both sides as the same base, so one-to-one property won't apply. Instead, we'll rewrite this in logarithmic form. We get the natural log of 813 over 643 equals 10k, and then we'll divide both sides by 10. This gives us k equal to the natural log of 813 over 643, all that divided by 10. We'll plug this into our calculator and get a decimal approximation that will round to 5 decimal places. We get k to be equal to 0.02346. And then we will rewrite our equation by plugging k and a sub 0 into our exponential growth model. That gives us the function a equals 643 times e to the 0.02346 t power. This is the function that we'll use to answer the question posed in part B. In part B, we want to find by which year will Africa's population reach 2,000 million or 2 billion. The reason they said 2,000 million here is because our original two amounts were in terms of millions. So when you plug in for your A, you have to be in that same unit of millions. The equation that we got in part A equals 643 times e to the 0.02346 t power is what we're using. We want to find t because it said by which year. And they're telling us that the amount A is 2,000. So let's plug that 2,000 in. 2,000 equals 643 times e to the 0.02346 t power. We start by isolating the exponential. We'll do that by dividing both sides by 643. 643 does not go into 2,000 even, so we're going to keep the fraction and not round with a decimal. The one-to-one property won't apply here because we're not going to be able to rewrite both sides. It's the same base. So instead, we'll rewrite it as a log. We get the natural log of 2,000 over 643 is equal to 0.02346 t. And to solve for t, we'll divide both sides. We get t equal to the natural log of 2,000 over 643, all that divided by 0.02346. Let's plug this in our calculator. When we do so, we get about 48.37. This is an application problem, so we want to make sure that we've answered the question. They want to know by which year is Africa's population going to reach 2 billion? Well, we got an answer of 48.37. Recall that T represents the number of years after 1990. So we need to go 48.37 years after 1990. That's 48 complete years, and then we're pushing into the 49th year. So we're actually going to get the year 2039. That first example was exponential growth. Now we're going to talk about exponential decay. One of the most common types of exponential decay are half-lives. We see that in chemistry. The half-life of thorium-229 is 7,340 years. How long will it take for a sample of this substance to decay to 20% of its original amount? We'll round our K value to 6 decimal places. Well, the first thing I want to mention is this 229. that doesn't do anything for us. That's just an isotope number that tells us what kind of thorium we're dealing with. So that's not going to be a number that's involved in our equation. We use the same decay model. It's the same as the growth model. We'll be using the equation A equals A sub 0 times e to the kt power. In our first sentence here, we are told that the half-life is 7,340 years. So this is our t, but notice that they didn't give an initial A or an amount A either. Now, this is something that we just have to remember about half-life. Half-life is how long does it take for half of the substance to go away? Well, here for thorium-229, it takes 7,340 years. But that's true that half of it's going to decay whether you have 1 pound of it or 1,000 pounds of it. Because of that, we can just choose the initial A to be any number you want. I always choose that A sub 0 to be 1. All right, so our initial amount is 1. And our A will always be 1/2 then, because this is half-life. Half of it is going to disappear. That's why I like to start with 1, because then it's easy. A sub 0 is 1, A is going to be 1/2. Now we have A sub 0, and T. We can plug it into our equation and solve for K. 1/2 equals 1 times e to the k times 7,340 power. I'll clean up that right side. I don't need the 1 in front since 1 times anything is that thing. And then I'll rewrite my exponent, 7,340k. We're solving for k. It's in the exponent, so we're solving an exponential equation. We have an exponential equal to a constant. We are ready to rewrite it in logarithmic form. This becomes the natural log of 1/2 equals 7,340k. And then to solve for k, we'll divide both sides by 7,340. This means that k equals the natural log of 1/2 divided by 7,340. We'll plug this in our calculator and round to 6 decimal places. Note, for plugging it into your calculator using 0.5 would probably be easier than 1/2. Either way, we get a k value of negative 0.000094. Notice in this example, our k is negative. That's because we have a decaying entity in this example. In the previous example, our k was positive because we had a growing entity. Now we're going to rewrite our equation. Since the initial amount was not given, we're not going to plug an initial amount in when we rewrite our formula. We're going to just write A equals A sub 0 times e to the negative 0.000094t. We have written the model. Now we're going to use this model to find out how long it would take for a sample of this thorium-229 to decay to 20% of the original amount. We'll be using the equation we came up with to answer this question. Well, again, they don't give us an initial amount. So I'm going to choose A sub 0 to be 1 again. Well, let's think about what A would be. Here, it's asking us how long it will take for this sample to decay to 20% of the original amount. So what's 20% of 1? 0.2. So we'll plug a sub 0 and a in and solve for t. We have the equation 0.2 equals 1 times e to the negative 0.000094 t power. We don't need the 1 in front of the e. We have an exponential on the right and a constant on the left. We're ready to rewrite it in logarithmic form. We get the natural log of 0.2 equals negative 0.000094 t. To solve for t, we'll divide both sides. We get t to be equal to 17,129.68. So how long is that? We'll say 17,122 years.